Hi, in this lesson we want to talk about the exponential function. Now the exponential function has quite the complicated looking format. We have a, we have b, we have p, and we have q. Now what do all of these variables do? First of all, we're going to take a look at all of them using the following diagrams. So we have the first one, a normal exponential function as we would expect. Then the second one, a reflected exponential function. Let me draw that a bit better. Something like that. Then a reverse exponential function. And then a reversed exponential function that is reflected. Like that. So what do all of these, how do all of these different graphs represent the different variable sets that we can have? So a is greater than 0 because our graph is above the x-axis, or rather our graph increases as x increases. Then for this one we can say that the a will be smaller than 0 because our graph is decreasing as x is increasing. So 1 is above the x-axis and is increasing as x is increasing. This one is decreasing as x is increasing. Then we take a look at the next one. So in this one, a is still greater than 0. Let me write it here. A is still greater than 0 in this one. This is because the graph is still above the x-axis, and here a is smaller than 0 because the graph is below the x-axis. Then we take a look at the next variable in question, which is b. In this case, b will be greater than 1. If b is greater than 1, it means that the function is growing exponentially, right? So if we have 2 over here and we keep on increasing this value of x, that means we're going to get bigger and bigger numbers. We'll get 2, we'll get 4, we'll get 8, 16 going on. So these numbers are going to grow exponentially. And in this case, that would be true as well. B is still greater than 1 in this case because we are growing exponentially, albeit negative or in the negative direction. We are still growing as x is growing, but growing in the negative direction. Then we come to this example. In this case, we say b is in between 1 and 0. So what we're basically saying is that b is a fraction. So if b is a fraction and we raise it to increasing values of x, such as 1, then 2, then 3, we're going to get a half, we're going to get 1 over 4, which is a quarter, we're going to get 1 over 8, 1 over 16. So as you can see, the values keep on getting smaller as x is increasing. And we can see that's the trend. As x is increasing in this direction, the values of y are getting smaller and smaller and smaller. And for that reason, we can also assume that this third function has the same property of b being between 1 and 0, basically b being a function, because again, as x is increasing in this direction, we see that our function is approaching the x-axis, or is approaching y is equals to 0. Then that is it for a and b. What about p and q? If we say minus p onto this function here, the first one, what our graph is going to look like is this. So we shift our function to the right by the value of p. And plus q, q is what is known as an asymptote. So an asymptote is a line that the graph will never cross or touch. It will just slowly approach that line in whatever direction that it is. So in this case, we can see that our asymptote for all of these examples, q was set to 0. But we can increase or decrease this value, and this has the effect of shifting our graph up and down as well. So you can also think about it as vertical shifts, except that you are shifting the graph in a manner that respects the asymptote. So as much as your graph is moving up and down at your will, it still has to respect the fact that it will not be able to cross or touch that line that you're shifting it to. For example, I can draw, if this is my Cartesian plane, I can have a function called y is equals to 2 to the power of x minus 4. This means that instead of having y is equals to 2 to the power of x with a function that looks like this, when we add this minus 4, we're basically shifting the asymptote, which was originally here, down to minus 4, if this is y is equals to minus 4. And then we have our function, which would look exactly the same as the one on top, except that it now has a different asymptote. And again, it won't cross this minus 4 line, just like it wasn't crossing the x-axis or the y is equals to 0 line. Then it's also important to note with these type of functions that it's not a guarantee that you will have an x-intercept. Like with a linear function, you always know that there's going to be a y-intercept, there's going to be an x-intercept. With the x-intercept in this case, it's not always a guarantee, because your function can have the asymptote at the x-axis, or it can have it above or below in such a way that it won't allow us to cross the x-axis. So don't be weirded out when you're trying to do a calculation and you find that you're unable to find the x-intercept for that function. But the y-intercept will always be guaranteed to be there. And that's it for this lesson on exponential functions.